Welcome to today's paper reading. Today's paper is titled SaySelf, Teaching LLMs to Express Confidence with Self-Reflective Rationales. This paper was published on the AR14 preprint by Tianyang Su and colleagues from Purdue University and other institutions. Large language models, LLMs, frequently produce inaccurate or fabricated information and often fail to indicate their confidence levels, which restricts their broader applications. Previous methods have attempted to elicit confidence from LLMs through direct or self-consistency prompting, or by constructing specific datasets for supervised fine-tuning. However, these prompting-based approaches have shown inferior performance, and training-based methods are limited to binary or inaccurate group-level confidence estimates. In this work, the authors introduced SaySelf, a novel training framework designed to teach LLMs to express more fine-grained confidence estimates. Additionally, SaySelf goes beyond confidence scores by initiating the process of directing LLMs to produce self-reflective rationales that identify gaps in their parametric knowledge and explain their uncertainty. This is achieved by using an LLM to automatically summarize uncertainties in specific knowledge through natural language, based on the analysis of inconsistency in multiple sampled reasoning chains. The resulting data is then used for supervised fine-tuning. Furthermore, the authors employ reinforcement learning with a carefully crafted reward function to calibrate the confidence estimates, encouraging LLMs to deliver accurate, high-confidence predictions and penalizing overconfidence in erroneous outputs. Experimental results show that SaySelf effectively reduces confidence calibration error while maintaining task performance. The generated self-reflective rationales are also reasonable and can further contribute to calibration. The code for this work is publicly available at the provided GitHub link. The introduction of this paper highlights the challenges faced by large language models, LLMs, such as the production of fabricated information and the difficulty in indicating uncertainty. Previous methods for eliciting confidence from LLMs, including prompting-based and training-based approaches, have been found to be suboptimal, often resulting in poor calibration performance and long inference latencies. In contrast, the SaySelf framework is introduced to address these issues by generating more accurate and fine-grained confidence estimates. It also enables LLMs to produce self-reflective rationales that explain their confidence levels, thereby reducing inference time and improving the overall reliability of the models. Figure 1 illustrates the contrast between SaySelf and previous methods in eliciting confidence from large language models, LLMs. SaySelf stands out by producing self-reflective rationales that not only explain the model's uncertainty but also provide fine-grained and accurate confidence estimates. This approach significantly reduces inference time compared to previous methods, which often suffer from poor calibration performance, coarse-grained confidence levels, and increased latency. In the related work section, the focus is on three main areas: confidence elicitation, hallucination and uncertainty expression, and explainability. For confidence elicitation, previous research has explored both prompting-based and training-based approaches. Prompting-based methods guide LLMs to generate confidence scores or use consistency levels as indicators of confidence. Training-based methods involve supervised fine-tuning using specialized datasets. SaySelf addresses the limitations of these methods by generating more accurate and fine-grained confidence estimates. Regarding hallucination and uncertainty, LLMs often generate information not supported by their training data, leading to a loss of trust. Research has aimed to explore causes and develop detection or mitigation methods. SaySelf is proposed as an efficient method against hallucinations by training LLMs to express accurate confidence estimates and self-reflective rationales. Lastly, in the area of explainability, previous work has focused on generating natural language explanations for LLMs' decision-making processes. SaySelf differs by generating rationales that justify predictions and elucidate confidence estimates, using LLMs' internal reasoning processes rather than human-annotated explanations. SaySelf is a training framework designed to teach large language models, LLMs, to express fine-grained confidence with self-reflective rationales. The framework consists of two essential stages: supervised fine-tuning and reinforcement learning from task supervision. In the supervised fine-tuning stage, a dataset D is constructed, containing questions Q answers with reasoning chains S, self-reflective rationales R, and confidence estimates C. This dataset is built from multiple sampled responses from LLMs, specifically using 90K questions from HotPotQA. Responses are clustered into K representative clusters based on semantic similarity. The confidence estimate C is derived from the cluster size of the correct response, and the self-reflective rationale R is generated by analyzing inconsistencies in the responses. In the reinforcement learning stage, a reward function is used to calibrate the confidence estimates, encouraging high confidence in accurate responses and penalizing overconfidence in incorrect ones. The proximal policy optimization (PPO) algorithm is employed for training. Implementation details include setting the sampling time N to 100, the similarity threshold T to 0.9, and learning rates and batch sizes for both stages. Figure 2 provides an overview of the SaySelf training framework, which consists of two essential stages: supervised fine-tuning and reinforcement learning from task supervision. In the supervised fine-tuning stage, a model-specific dataset is established, containing self-reflective rationales and confidence estimates derived from multiple sampled responses from LLMs. This stage aims to train LLMs to generate accurate self-reflective rationales and confidence estimates. The reinforcement learning stage uses a carefully designed reward function to further calibrate the confidence estimates for each instance, ensuring that LLMs produce more accurate and differentiated confidence levels. The framework is designed to significantly reduce the confidence calibration error and maintain task performance, enabling LLMs to express fine-grained confidence with self-reflective rationales. The evaluation of large language models, LLMs, was conducted using several datasets designed to test different aspects of model performance. These include HotPotQA, which focuses on multi-hop reasoning, Truthful QA for assessing the truthfulness of model responses, and Strategy QA for true/false questions requiring multi-hop reasoning. The primary metrics used to evaluate these models include the expected calibration error, EC, to measure confidence calibration, the area under the receiver operating characteristic, OROC, to distinguish between correct and incorrect responses, and accuracy to gauge task performance. The main experimental results indicate that SaySelf significantly outperforms other approaches in reducing calibration error and improving the distinction of confidence in responses. These results are consistent across in-distribution and out-of-distribution datasets, demonstrating the general applicability of SaySelf. Additionally, the differences observed are statistically significant, further highlighting the effectiveness of SaySelf in providing accurate confidence estimates. Table 1 presents the EC evaluation results for various methods including SaySelf and its ablations. The table shows that SaySelf significantly reduces calibration error, EC, compared to all baseline approaches, with a notable advantage statistically significant at p less than 0.05. This performance is consistent across different datasets, with HotPotQA being the only in-distribution dataset evaluated. The table also differentiates between SaySelf with and without reinforcement learning, without RL, without self-reflective rationales and confidence estimates, without RNC, without self-reflective rationales, without R, and using a naive reward function, W/naive-RF. The results underscore SaySelf's effectiveness in providing accurate confidence estimates. Table 2 presents the accuracy evaluation results of various methods including SaySelf and its ablations across different datasets. SaySelf demonstrates the ability to maintain the original task performance, indicating that the task of confidence estimates does not conflict with the original task. SC, which uses multiple sampling, achieves overall better performance compared to other approaches but results in high inference latency. SaySelf significantly outperforms all baseline approaches in reducing the calibration error, EC, and improving the distinction of confidence in correct and incorrect responses, OROC, as observed in both in-distribution and out-of-distribution datasets. Table 3 presents the faithfulness evaluation results for self-reflective rationales. The data indicates that SaySelf can generate more reasonable self-reflective rationales that reflect internal uncertainty in LLMs, as evidenced by inconsistencies across multiple sampled responses. An exception is the Strategy QA dataset, which, due to its true/false question format, results in high variance in evaluation. Additionally, a Spearman's rank correlation coefficient of 0.89 between GPT-4 and human ratings demonstrates the reliability of GPT-4 for automatic evaluation. Table 4 presents the confidence levels in the unanswerable and answerable subsets of the Squadron dataset. It highlights that SaySelf significantly reduces confidence in unanswerable questions while maintaining confidence in answerable questions, achieving the best confidence gap between these subsets. Figure 3 presents a case study demonstrating SaySelf's ability to generate insightful self-reflective rationales that effectively capture the internal uncertainty in LLMs. The figure showcases various clusters derived from a selection of 100 sampled responses, with the rationale being generated by the LLMs themselves. This capability highlights SaySelf's effectiveness in understanding and expressing the inherent uncertainties within large language models. The SaySelf framework presented in this paper aims to improve the accuracy and granularity of confidence estimates and self-reflective rationales from large language models, LLMs. Through supervised fine-tuning and reinforcement learning, SaySelf has been shown to reduce calibration errors and maintain performance across various datasets. However, there are risks associated with this approach, such as the potential for users to over-rely on the model's confidence estimates, which could lead to harmful decisions if these estimates are inaccurate. Additionally, the framework's effectiveness is partly dependent on the quality of chain-of-thought reasoning, which is still a subject of debate in the research community. Ethically, this work uses publicly available datasets under various licenses and ensures that data is anonymized to avoid privacy issues. Human annotations were used for analysis, with all parties agreeing to this as a voluntary service. This work is supported by the U.S. National Science Foundation, and any conclusions drawn are those of the authors and not necessarily the views of the NSF. Thank you for watching.